everyone, my name is Lydia, and this is what I wish they taught me about econometrics and introduction. So far, we've focused on two things: getting the right variables for the model, and we've discussed that under the omitted variable bias issue. So, getting the right variables. And we've also looked into dealing with correlated regressors, a problem that we called multicollinearity. Okay. Now we ask a different question. Even if our coefficients are right, can we trust our inference? And that depends on a very important assumption about the errors. We've seen this assumption before when we've talked about the OLS assumptions for the statistical properties. But let me remind you, this assumption is the homoskedasticity assumption that the conditional variance of the error term on the x variables included in your regression is equal to sigma square. Okay? So the variance of the errors is constant for all values of x, which means it doesn't matter whether x is large or small, the spread of the errors around the regression line is always the same. Okay, and this is what we called also homoskedasticity. This video is about what happens when it fails, because so far we've seen in the previous videos why do we need it and intuition behind it. So make sure you check those videos once again if you have forgotten. But when this assumption fails, it means we have heteroskedasticity. So what is heteroskedasticity? Well, in heteroskedasticity, this conditional variance is not equal to sigma square, which means that the spread of errors changes with the values of x. Okay? And one of the pictures that most of you will always think about when you think of heteroskedasticity is the funnel-shaped one. But if you don't remember it, and if you want to get a visual clue of what heteroskedasticity would look like, the best way to do it is set your regression line. You know, this is the one that you would have estimated. And then, as we said, the spread of errors changes with the values of x. So for small values of x in here, you can imagine that you have clustered observations. And then for large values here, you have a larger spread of what is happening. Okay, so as you can see, ultimately, there is that famous funnel shape that you have seen before, or the fan shape, and the classic visual signature of heteroskedasticity. You can think of real life implications or examples. For instance, income and consumption spending. Low-income households, spending is predictable because most of it will go to necessities. High-income household spending is much more variable, with some saving a lot and some spending a lot. So the variability in consumption will increase with income, and that's what like heteroskedasticity would show in if we were to plot that kind of data. So the spread of the errors will depend on the x, in which case would have been income. Okay. However, what are the things that heteroskedasticity does not change? What does? The regression line is still correctly estimated when you have heteroskedasticity. So OLS coefficients are still unbiased and consistent under heteroskedasticity. Okay, so it does not affect point estimates So beta 1 hat is still centered on the true beta 1. And this surprises a lot of students. So keep in mind, with heteroskedasticity, the problem is not with the OLS estimates. It's how OLS measures the uncertainty around those estimates. Okay? So then what does change? That's the most intuitive follow-up question. So what does change? In this particular case, so the problem will be with standard errors. Okay, so when heteroskedasticity is present, standard errors are wrong, usually small, like too small, which means that confidence intervals will be narrow and sometimes too narrow. T-tests cannot be trusted because they will give misleading results. And p-values as well cannot be trusted. So as you can see, it's like a whole cascade of consequences. And you might think a coefficient is significant when it isn't. So it means that you're genuinely looking at the wrong result, whether your beta hat is statistically significant or not. The direction of the bias in standard errors depends on the form of heteroskedasticity. So they can be too small or too large, but in practice they are more often too small, leading to basically overall rejection of the null hypothesis. OLS assumes all observations are equally informative about the regression line. Under homoskedasticity, that's true. Every observation has the same error variance, but under heteroskedasticity, some observations are much noisier than others. And OLS does not account for this because it weighs all observations equally. So its measure of uncertainty is going to be wrong. And that is the core intuition about why we don't like heteroskedasticity, because noisy observations should count less. OLS doesn't know that, and so its standard errors are miscalibrated. Okay? So I'm going to write this here for you so you don't forget it. So noisy observations should count less. OLS doesn't know that. And the consequence is standard errors miscalibrated. So where heteroskedasticity fits in the bigger picture in econometrics in general. So we've now seen with heteroskedasticity 3 distinct problems, okay? So with OVB, we saw that we have wrong coefficients, okay? Which means that we have systematic bias in point estimates. And we've got multicollinearity, which gave us imprecise coefficients. Okay, so in here we had large standard errors, okay? But we still got the right answer on average. Then ultimately we have heteroskedasticity, where we've got wrong inference, meaning coefficients are fine, but standard errors are not. Okay. So each problem attacks a different part of your result. And knowing which problem you have tells you exactly then the way you have to fix it. Just like we've seen with OVB and multicollinearity, we'll also see the way to fix heteroskedasticity. Heteroskedasticity, again, means non-constant error variance. It leaves coefficients unbiased, but makes standard errors wrong, so inference cannot be trusted. In the next video, we'll see exactly how heteroskedasticity distorts standard errors and what the consequences are for hypothesis testing. So stay tuned, and I'll see you in the next video.